All right, guys, in this lesson we're going to be looking at sampling distributions, and if you kind of remember, when we look at sampling distributions, we have two types. So the first that we're going to look at is sample proportions. That's the first type of sampling distribution that we're going to be looking at. It's just based off of proportions. So if we start with a population with a proportion P and take all the samples of size N, then the sampling distribution can be considered approximately normal if we are told that the population is normal or the large counts condition is met, where the total number in the sample times the proportion, or the proportion for success, is greater than 10, and the total number in the sample times the proportion for failure is greater than 10 as well. And our mean, or just our sample proportion, essentially is going to be equal to the population proportion, and our sample standard deviation for proportion is going to be equal to the square root of our proportion for success times our proportion for failure divided by the total number in the sample. So that's how we find all of that. So let's look at this example real quick. It is estimated that 80% of people with high math anxiety experience brain activity similar to that experienced under physical pain when anticipating doing a math problem. In a simple random sample of 110 people with high math anxiety, what is the probability that less than 75% experience the physical pain brain activity? So we essentially want to solve these three parts of the problem in order to figure out the actual probability that less than 75% experience the physical pain brain activity. So first we need to understand whether or not it's normal. Because we're not told that it's normal, we need to check our large counts condition. So we know that there's 110 people total in the simple random sample, and we need to test that with the actual proportion itself. And so we take 110 times 0.8, that gives us 88, which we know is greater than 10. Then we also test it against the failure proportion as well, which is 0.2. So 110 times 0.2 gives us 22, which is also greater than 10 as well. So we can state that this distribution is approximately normal by the large counts condition. Next, we need to find our mean and standard deviation for this sampling distribution. And so again, our mean for this proportion, or the sample proportion, is essentially just the same as the population proportion, which is 0.8. And our standard deviation is going to be 0.8 times 0.2 divided by the total number in our sample, because that's the percentage for success and the proportion for failure. We take the square root of that, and that gives us 0.0381. So that's our standard deviation, our sample standard deviation for this proportion. From there, we want to try and figure out the probability that less than 75% experience the physical pain brain, and we can do that a couple ways. First, we can figure out our z-score, which is going to be the actual proportion that we're figuring out, which is 75%, minus the population, or the sample proportion itself, which is 0.8, divided by the standard deviation, which is going to give us a z-score of negative 1.312. Then we would find the p-value, or the proportion, when z is less than that, which would give us this value right here. What we can also do is we can go to our calculator, and we can go to second vars, and then we can select normal CDF. So normal CDF. And then because we are trying to determine whether or not, we're trying to determine the probability that less than 75% experience the physical pain brain activity, what we can do is we know that we have a lower bound and an upper bound in our normal CDF function. Well, if we're trying to find the probability that less than 75% experience something, then that 75% is going to represent our upper bound. So our lower bound is going to be a very low negative number. Our upper bound is going to be 0.75 in this case, because that represents 75%. Our mean would be 0.8, and our standard deviation would be 0.0381. And when we plug that in, let's make sure that that works. When we plug that in, we should get an answer that is very similar to this. I got 0.0947, but 0.0947 will work just fine when you're looking at this. So that is another function that you can use to determine what it is we need to determine in this problem. Okay, we also have our second category of sampling distributions, which is sample means. And so we have proportions and means. If we start with a population with a mean of mu and a standard deviation of theta and take all the samples of size n, then the sampling distribution can be considered approximately normal if we are told that the population is normal or the sample size is significantly large for the central limit theorem to apply, and we will discuss that again in a moment, or we graph the data and determine it to be normal. So there are a few ways that we can figure out whether or not that's going to be normal. Again, the sample mean for this is going to represent or equal the population mean, so there's really no difference between those two as well. Whereas the sample standard deviation is going to be the population standard deviation divided by the square root of the total number in the sample. Okay, so let's take a look at this example right here. It is estimated that the cats who live in the wild or as indoor pets allowed to roam outdoors kill an average of 10 birds a year. Assuming a normal distribution with a standard deviation of 3 birds, what is the probability a simple random sample of 25 cats will kill an average of between 9 and 12 birds in a year? So again, we are told that this is a normal distribution right here, so we don't need to test the central limit theorem, we don't need to graph, we really don't need to do anything. We're just told that it's normal, so we're good to go. When we want to determine the mean or the sample mean for this problem, we know that that represents our sample mean is going to represent our population mean, which on average they kill about 10 birds a year. And our sample standard deviation is going to be represented by our population standard deviation, which is at 3, divided by the square root of the total number in the sample, which is 25, which gives us a sample standard deviation of 0.6. From there, we can determine what the actual question is asking, which is the probability that they will kill between 9 and 12 birds in a year. Again, we can do this a couple ways. We can find 2 z-scores because, again, we're trying to determine something between 2 numbers. So we can determine the z-score for 9, which is negative 1.667, and the z-score for 12, which is 3.33. And then we can find the probability of a z-score between negative 1.67 and 3.33, and that gives us that probability right there. Again, we can also use second vars and our normal CDF function to determine this probability. So again, if we go to second vars, our lower bound is actually going to be represented by the 9 in this case. So that we can type 9 in for our lower bound. We can type 12 in for our upper bound. And then from there, our mean, again, is represented by the 10, or the sample, or the population mean, and our standard deviation is represented by 0.6, because that is what we calculated in this case. And then if we plug that in, we get an answer that's actually the exact same as 0.952. So that is another way, and probably the way that I would solve this if you get a problem that is similar to this. So just remember second vars and normal CDF, and you should be good with this. Remember that our central limit theorem, hopefully you remember this, is if you take any population with a distribution of any shape and take a sufficiently large sample, then the sampling distribution will be approximately normal. And so in order for our central limit theorem to be met, the sample size, and this is only when we are looking at means or sampling distributions that have to do with means, not proportions. So if our sample size is greater than 30, it is considered to be a large sample. So again, only for means, not for proportions. So a naked mole rat, a hairless East African rodent that lives underground, has a life expectancy of 21 years with a standard deviation of 3 years. In a random sample of 40 such rats, what is the probability that the mean life expectancy is between 20 and 22 years? Now, because we were not told in the problem that the sampling distribution would be normal, we have to check either a graph or the central limit theorem. And since our sample is 40, which is greater than 30, then it is met by the central limit theorem. So we can consider this distribution to be normal, or our sample distribution to be normal. From there, we can determine our mean and standard deviation, which our mean, again, just represents our population mean of 21 years. Our standard deviation represents our population standard deviation divided by the square root of the total number in the sample, which is 40, and that gives us a sample standard deviation of 0.4743. And then from there, we can determine what the probability is that they will live between 20 and 22 years. You can do the method above, or once again, second vars, normal, CDF. And again, we are trying to determine the value between 20 and 22 years. So 20 will represent our lower bound, 22 will represent our upper bound, our mean will represent 21, and our standard deviation will be 0.4743. 0.4743, and that gives us a value of 0.965, which is exactly what we got if we worked out the z-score. So once again, normal CDF comes in super handy for this. We also have this idea of a difference of proportions. So moving past just finding the sampling distributions for proportions or just means, we now have the difference of proportions. So if we start with two populations with a proportion of P1 and P2 and take all the samples of size N1 and N2 respectively, then the sampling distribution can be considered approximately normal if we are told both populations are normal, and that has to be both populations of N1 and N2, not just one of them. Or the large counts condition is met for both populations, which is that the total sample size for our first population times its proportion and the total number of the population times its proportion for success are greater than 10, or their proportion for failure is also greater than 10 as well. We can determine the mean by simply taking the proportion of our population 1 times the proportion of population 2 and subtracting those, and that will give us our mean. However, with standard deviation, because even though we're doing a difference in proportions, we have to make sure that we add when it comes to standard deviation. So, and I have seen questions where they just ask you for the actual formula when it concerns this, and so it's very, very important to understand that when you, even though you're doing a difference in proportions, you are still adding when it comes to standard deviation. So how we do this is we take the proportion of success for sample 1 times the proportion of failure for sample 1 divided by the total number in sample 1 plus the proportion of sample 2 times the failure of proportion for sample 2 divided by the total number in sample 2, take the square root of all that, and that gives us our standard deviation for difference of proportions. Now let's take a look at this example. In a study of how environment affects our eating habits, scientists revamped one of two close to each other fast food restaurants with tablecloths, candlelight, and soft music. They then noticed at the revamped restaurant, customers ate slower and 25% left at least 100 calories of food on their plate. At the unrevamped garish restaurant, customers tended to wolf down their food, and only 19% left at least 100 calories of food on their plates. In a random sample of 110 customers at the revamped restaurant and an independent random sample of 120 customers at the unrevamped restaurant, what is the probability that the difference in the percentages of customers in the revamped setting and unrevamped setting is more than 10%, where the difference is the revamped restaurant percent minus the unrevamped restaurant percent? So again, we can state that both distributions are normal by the large counts condition. So we have two samples of two different sizes. We have one sample of 110 customers at the revamped restaurant and a sample of 120 customers at the unrevamped restaurant. And so we take 110 first, because we're taking the revamped minus the unrevamped, times our 0.25, so 110 times 0.25, which is his proportion for success, which is 27.5, and 110 times 0.75, which is his proportion for failure. Both of those are greater than 10. Our second unrevamped restaurant sample size is 120 times its proportion for success at 0.19 and 120 times 0.18. Both of those numbers are greater than 10 as well, so you have to make sure that you show work and check for all 10 numbers in order to prove that this is a normal distribution, a normal sampling distribution. The mean and standard deviation of the difference in proportions is found like so. So again, all we need to do is take the two proportions from the revamped restaurant and the unrevamped restaurant, subtract them, and that gives us a mean difference of 0.06 in proportions. And then our standard deviation is found like so, which we find out for our standard deviation of difference in proportions is 0.0574 in this case. So lastly, what we need to do is we need to find the probability that the difference is more than 10%. Okay, and so how we do that is we can also do that through normal CDF. Now we may have to use a bit more math to figure out our difference as far as this goes, but we can still use second VARs and normal CDF as well for this. Second VARs, normal CDF. Okay, now because we are checking to see if the probability of the difference is more than 10%, then that means that 10% is going to represent our lower bound. So we're going to enter in 0.10 for that, a very high number for our upper bound. Go ahead and type this in. Our mean is going to be represented by 0.06 and our standard deviation by 0.0547. So 0.06, 0.0547, we hit paste, and voila, we get the exact same proportion that we get up here at 0.2323. So there is a 23% chance that the probability, 23% chance that the difference in these two restaurants is more than 10%. Now, we also have a difference in means right here. So if we start with two populations with a mean of mu1 and mu2 and the standard deviations of theta1 and theta2 respectively, and take all the samples of size n1 and n2, then the sampling distribution can be considered normal if we are told both populations are normal, the sample sizes are significantly large for the central limit theorem to apply, and that means both sample sizes of n1 and n2, and we graph the data and determine it to be normal. And then we find our mean difference by our sample mean difference by just taking the population mean of 1 subtracted to the population mean of 2. That gives us our total difference in sample mean right there. And then our sample standard deviation is going to be represented by the standard deviation of 1, or the population standard deviation of 1 squared, plus the population of standard deviation 2 squared. And then both of those are going to be divided by the sample of population 1 and the sample of, the sample of population 1 and the sample of population 2. Right. All right, we're going to look at this example for sample means real quick, or difference in sample means. So it is estimated that 40-year-old men contribute an average of 65 genetic mutations to their new children, whereas 20-year-old men contribute an average of only 25. Assuming standard deviations of 15 and 5 mutations, respectively, for the 40 and 20-year-olds, what is the probability that the mean number of mutations in a random sample of 35 40-year-olds 40-year-old new fathers is between 35 and 45 more than the mean number in a random sample of 40 20-year-old new fathers. So essentially what we're doing is we are taking the mean of 40-year-old new fathers, or their mutations, and subtracting it from the genetic mutations from the mean of 20-year-old new fathers. So we have 35 total 40-year-old new fathers in the sample, which is greater than 30, and 40 20-year-old new fathers, which is also greater than 30 as well. So the central limit theorem will apply in this case to make our sampling distribution normal for the difference in means. And then when we want to find the mean and standard deviation, the mean is simply taking the total number of genetic mutations for 40-year-olds and the total number of genetic mutations for 25-year-olds and subtracting those, which would give us a total of 40, or a mean sample difference of 40. When we're looking at standard deviation, we take the population standard deviation for 40-year-old new fathers, which is 15, square that, divide it by the total number in the sample at 35, then add the population standard deviation for 20-year-old new fathers, square that and divide it by the total number in the sample at 40, then take the square root of all of that, and we get a sample standard deviation in this of difference in means of 2.656. Then we need to answer the probability that the mean difference is between 35 and 45 more in this case. So, again, second vars. And then we need to click on normal CDF. So second vars, normal CDF. And then our lower bound is going to be represented by 35, whereas our upper bound is going to be 45. So 35, then 45. Our mean difference is going to be 40, which is what we found above, with our standard deviation of 2.656. So 2.656. And then we can enter that, and we should get a probability of 0.94. So there's a 94% chance that the mean difference is between 35 and 45 more. So again, using normal CDF to help us is going to be a huge help. So last but not least, we have the t-distribution, which again is mostly used for just means. But it's also important to use when we are not given a population standard deviation. So since most cases of looking for population parameters will involve unknown population standard deviations, we will use standard errors instead of standard deviations. So the first thing that we need to understand is that a standard error is the standard deviation of the sample itself. And how we normally are going to find this is with t. So with t, we would take our sample mean minus our population mean divided by our sample standard deviation and divided by the square root of the total number in our sample. And that's how we find our t value in this case. We also need to understand what degrees of freedom is, and that's the difference between the standard normal distribution and the t-distribution gets smaller as the sample size gets larger. So how we find our degrees of freedom is taking the total number in the sample and subtracting 1. Then if we were going to find the standard error for just our population, or excuse me, our sample proportion, that would be the square root of the sample proportion times the sample proportion for failure divided by the total number in the sample, take the square root of that with degrees of freedom at n-1. And if we wanted to find the standard error for our sample mean, in that case, we would take the sample standard deviation divided by the square root of the total number in the sample with degrees of freedom at n-1 as well. So just in summary for all of this, provided that the sample size n is large enough, the sampling distribution of the sample proportions is approximately normal with a mean p and a standard deviation of the square root of p times 1 minus p divided by n, where p is the population proportion. Provided that the sample size n is large enough, the sampling distribution of means is approximately normal with a mean of mu and a standard deviation of theta divided by the square root of n, where mu and theta are the population mean and standard deviation. And then when the population standard deviation is unknown, which is almost always the case, and provided the original population is normally distributed, or the sample size n is large enough, the sampling distribution of the sample mean follows a t-distribution with a mean at mu and a standard deviation at a sample standard deviation divided by the square root of n, where mu is the population mean and s is the sample standard deviation.